Hey everyone. My name is Zach Hoylman. I'm really excited to be here today. I come from Missoula, Montana, Western Montana, where I'm a research professor at the University of Montana and the assistant state climatologist in the Montana Climate Office. And I was asked to come here today to talk about soil moisture data in our new drought delivery information tool called D3 Drought, or the drought data dashboard. And I don't have time to demo this dashboard for you today, but I am going to show you some of the functions and really hone in on some of the work we're doing with respect to soil moisture. And before I start, I just want to say that this work is really a representation of 10 years of co-production in the Upper Missouri River Basin and in Montana with many state partners, federal partners, some that are here. And we're codifying a lot of these relationships and kind of next steps in a NSF R2I2 project where we have a phase one award that we're calling the NGP Rider, or the Northern Great Plains Regional Incubator for Drought Resiliency. So I'm going to talk a little bit about that as well. But before I start, I thought I would just begin by giving you an overview of like what is D3, and this is our data delivery system. It's national scale, and at the end of the day, what we aim to do is just provide a ton of drought data in one easy access place. And not everything under the sun. We tried to be parsimonious. We've heard that here today, but provide a lot of information for people to access, including precipitation, temperature, snowpack, streamflow, soil moisture, and these are all nationwide and daily, including both modeled and in situ products. So there's a lot of data there. I encourage you to go check it out. And one of the key things is that it's open source and I think pretty fast. And we have transparent methods, code. It runs on any browser. It's really done client side. And you can do a whole bunch of cool customizations of, aggregations on the fly, et cetera. But at the end of the day, it also allows you to do what we're calling the convergence of evidence tool, which is a way to access multiple lines of inference to do an evaluation of where metrics agree, disagree, create custom blends, et cetera, with different weighting functions. So this is something that we're using now to seek towards a more reproducible and transparent drought assessment process in our region. What I'm going to talk about today too is that we have a bunch of new layers that are coming online that are all based on this idea of using knowledge-guided machine learning for things like streamflow, soil moisture. We're working on many other state variables. With shareable links, you can download georasters. Everything that we produce in the Climate Office is publicly available, and a lot of these data sets go back daily to 1982. And their national scope, right? We have this national dashboard, but what we found in Montana is that a key to success and adoption is retaining local flavor. And we see that with our Governor's Drought and Water Supply Advisory Committee, which is meeting as we speak right now in Helena, Montana. Having that local flavor of Montana-specific data sets is something that really drives adoption and builds kind of trust in these products. And so we've come up with this idea of how do we create a tool that's national in scope, but allows for that flexible local flavor. And I think we found something that's kind of cool. And if you're a nerd like me, you love to understand kind of what's going on in the background. And what's super cool about this dashboard is that we're doing a bunch of stuff in a pre-computed environment. That's all happening on the cloud. We're using Dockerized containers. If you guys understand what that is, they're basically little micro computers that you can spin up and destroy in seconds. We do that all through Elastic Container Services through AWS Fargate, and they're passed through high egress S3 buckets on Amazon so that we don't deal with the power outages and stuff like that happen at the university all the time, disrupting data services. So we found this kind of this new modern way of delivering this data. Like I said, this is really an expression of the data delivery capabilities that we're seeking to provide through this NSF project, the NGP Rider project, which is, again, an NSF R2I2 Regional Resilience Innovation Incubator, I think is the acronym. This is a phase one award. We're working towards the phase two, where we're bringing together all of this coalition of many folks across the Upper Missouri River Basin, including state mesonettes. We've got Nathan in the back over here as a part of the project, state climate offices, universities, national partners, private sector, insurance companies, to try to build a more resilient and modern drought assessment system in the Northern Great Plains to promote that resiliency. So if you're interested in this project, I'd be happy to talk more about it. But I think one of the key, and we've heard it here quite a bit, fundamental kind of questions and challenges that's really exciting is how do we take these incredible growing networks like the Montana Mesonet, which is a part of this Upper Missouri River Basin network, which you can see here. Any one of those green squares is a location where we have a station reporting currently 5-minute intervals, lots of soil moisture data, all the atmospheric stuff, and we're installing those blue stations this year, and we'll finish up the project next year with those orange squares. And the question is, how do we provide these kind of like bespoke state level networks into a national framework that allows you to access that information if it's interesting to you, but doesn't kind of clutter up the whole system at a national scale? And so the way that we've done that is by implementing what we're calling like a flexible local plugin support system, which effectively allows you to access Montana data. If we were to partner together, we could access, say, data from Alabama or data from Louisiana. We saw that information that might be really useful for your drought assessment product. And the way we do that is with using something that's called a contextual activation function, where effectively, as you zoom in, and I could show you this if I had time, zoom into Montana. If it populates enough of your viewport, that data is then accessed. You get proper attribution that's very clear, that is customizable, allows you to access that data in coordination with a state climate office, a university, et cetera, and is really something that's scalable across CONUS and allows for this flexibility. So we're really excited about that. And defining and describing, showing this point level data is only one way that we can acknowledge the useful information that's being collected from these systems. Another way is to integrate them more broadly into our structural assessment gridded systems, right? And the way that we're going to do that here in Montana and across the region really is by using something that we're calling knowledge-guided machine learning. Actually, the keynote speaker referenced a great paper from some of the foundational kind of work on that stage. And the way that we do knowledge-guided machine learning is first by doing some good old-fashioned basic science, where we're looking to find which models perform really well. So we did a paper in WRR a couple of years ago that identified, for example, the Sport LIS system, Jonathan Case is in the back over there, as one that's very good at detecting drought dynamics compared to many other systems. We tested 9 different models: CPC, SMAP, TopoFire, NLDOS, et cetera. And Sport was found to be really, really performant. So what we do is we take a deep neural network to basically train the neural network to understand the physics that are embedded within Sport LIS. As a prior, if you guys are into Bayesian statistics like me, it's kind of like a good way of thinking about an early idea, an early prediction, right? This is our first case. And we can do that really broadly across the United States. Then what we can do is encode actual observations using Mesonets or USCRN, SNOTEL, SCAN, et cetera, to basically correct for structural deficiencies in the model and bias corrections of the model. We can start playing fun games like, well, if we add 3 stations, 10 stations, 100, 200, 300, how is accuracy increasing? And see how increasing numbers of stations included in these modeling frameworks increases accuracy. Do these big assessments, see how we're doing. Anywhere that's purple on that map represents really noticeable gains in KGE, which is not the Kling-Lupta efficiency. It's correlation, variability, and bias. Then we can take that and do a reanalysis, so we can back predict soil moisture going back to 1982. And what's super cool is you can use really short periods of record in the more contemporary season, right? Say 21 to 2026, or even just a single year. And that will actually help to structurally correct the model errors going back in time very far. So you can use short-lived periods of record to create much more accurate long-term representations of soil moisture dynamics. And then we need to operationalize it and turn it into a product that's just not just data, but information. This is just a super quick GIF that shows you the 2025 summer, shallow on the left, mid depth on the right. And you can see these lags, that low pass filter that we were already hearing about. And what's really cool about these neural networks is that once we've trained them, and it takes a while to train, you can operationalize them really quickly and make really large predictions relatively quickly. Then, of course, as we've heard, we have to convert that into a usable piece of information. So here we take our 30-year climatology, which we just heard about from Ronnie. We use a beta distribution to fit a parametric probability distribution to that data, compute the percentile, turn it into a standard normal Gaussian distribution using inverse Gaussian function. And now we can display that on our drought dashboard using 30-year climatologies that give us kind of that natural drought speak that we're all used to seeing in terms of drought classes, right? And so echoing what our keynote speaker said, I would just like to end by saying that, in my opinion, drought is fundamentally a state variable problem. It is not a meteorological proxy problem. And I think that the future of drought assessment in our country really needs to hone in on this idea that state variables are what we care about. And for this speak, right, soil moisture knowledge is key to assessing and diagnosing and responding to that drought condition across the nation. And I think that this expands beyond just soil moisture. That's one key state variable, but things like stream flow, groundwater, evapotranspiration, all of these state variables and fluxes are really what we care about. And I encourage us to really try to hone in on making as much use of the information that we're collecting across this nation to really move in that direction, as opposed to using things like meteorological proxies. So with that, I'll say thank you very much, and thank you.